So in this lesson, we're actually going to learn how to interpret the equilibrium constant to understand what exactly it tells us about the equilibrium reaction. And then we're also going to learn how to work with the equilibrium constants, specifically learning how to manipulate them in order to study the reactions that we're concerned with. So first of all, let's talk about the magnitude of equilibrium constants. Well, if your equilibrium constant is a lot larger than 1, what that tells you is that the equilibrium lies to the right. And since your numerator represents the products, that means that you have more product being formed than reactant. So what we say is that you can either say the equilibrium lies to the right or simply that the products are favored in the equilibrium reaction. If your equilibrium constant is less than 1, what that tells you is that the equilibrium lies to the left, meaning that your reactants are favored because remember again, reactants are in the denominator, and therefore if your K is less than 1, that means that the denominator value is larger than the numerator value. Now that we've talked about the quantitative value of your equilibrium constant and what that tells you about whether your products or your reactants are favored, I'm now going to show you ways in which you can manipulate equations and therefore how to manipulate your equilibrium constant. So this is the Haber process, nitrogen reacting with hydrogen to form ammonia. And the first question in A simply asks you whether products or reactants are favored. So let's review how you determine that. Well, first I have to actually calculate my equilibrium constant. So I know that my Kc, my equilibrium constant, equals my concentration of NH3 squared all over my concentration of N2 times my concentration of H2, and I'm going to cube that. Now I'm just going to plug in my values because I know all of my different concentrations. So into this, for the concentration of NH3, I have 2.1 times 10 to the negative second. I'm going to square that all over the concentration of N2, which is 8.5 times 10 to the negative first, times the concentration of H2, which is 3.1 times 10 to the negative third, and I need to take that value and I need to cube that. And so what I end up getting for my Kc is that it equals 17,415. Okay, so I'm going to round this to the correct number of sig figs. I'm going to just say 17,000 is what my Kc equals. Now, since this is much larger than 1, what that tells me is that the concentration of products, of what has been produced by products, is much greater than for the reactants, which means that my products are what are being favored in this equilibrium reaction. Right? Now let's actually see how I can manipulate this Haber cycle process, this reaction, and what I need to do in order to calculate my equilibrium constant as a result. So if you look at B, what you should notice is that this reaction right here is just the exact opposite of the reaction I had above. So my Kc for this is going to be equal to the concentration of N2, because that's now my product, times the concentration of H2, that's going to be cubed all over the concentration of NH3, and that is going to be squared. Now what you should notice, this versus this, well, how does my Kc here compare to my Kc here? Well, this Kc, to get this equal to this, all I need to do to my Kc and to this is just flip it. So my Kc, this is actually just going to be equal to 1 over this Kc will give me this equilibrium constant. So what that tells me is if I flip a reaction, what you have to do to the equilibrium constant, you just have to find the reciprocal of it. You have to flip it as well. So if you flip a reaction, then the equilibrium constant, so the Kc, is going to be equal to just the reciprocal. because all you have to do to get the original equilibrium constant is flip this reaction, so that's all you got to do to your Kc. Now, let's look at what happens if, notice here, all I've done is I've multiplied all of my coefficients by 2. That's the only way it's different from A. So if I find my Kc of this guy, I know that this is going to be equal to NH3, instead of squared now, it's going to be raised to the 4th, and then this is going to be N2 squared, and then this is going to be H2 to the 6th. And so if I want to get this equilibrium expression looking like what it did in A, what I could actually do is take NH3, square it all over just your N2 times your H2 cubed, but then take the entire expression and square it, because then I would get NH3 to the 4th, N2 squared, and H2 to the 6th. So what I'm going to end up doing to my equilibrium constant is I'm going to raise it to whatever value I multiplied my entire reaction by. So you're going to raise it to the number that multiplied reaction by. Now, I'm going to go over this again at the very end of this video, but there are just 2 ways that I can manipulate a reaction. Let's now look at another example, but in this case, I'm not just going to be flipping reactions or multiplying them by a constant. I'm actually going to be adding up reactions, just like I did with Hess's law. All right, so if you look at this example right here, it gives you the reaction. Oxygen reacts with oxygen to form ozone. And then it actually gives you just 2 different reactions with your KEQ. So this should bring up memories of Hess's law quite a bit. What I want to do is I want to sum these 2 reactions together in order to get this final reaction, which is exactly what I did with Hess's law, except now I'm dealing with my equilibrium constant. All right, well, I want oxygen with the monatomic oxygen on my right-hand side, on my reactant side. So what that tells me is that I'm actually going to want to flip this reaction above. So I'm going to flip it quickly. And so in order to flip it, remember, when you flip a reaction, the equilibrium constant, you just need to find the reciprocal of that. So I'm going to take 1, and I'm going to divide it by 6.8 times 10 to the negative 49th, and I end up getting 1.5, or 1.47, times 10 to the 48th. Okay. Now, if you look here, I want O3 on my product side, so I'm going to also have to flip this reaction. So I'm going to do NO2, reacts with oxygen, and it forms O3 and NO. All right, so since I flipped this reaction, what that tells me that I need to do is I also need to flip my equilibrium constant by finding the reciprocal of it. And so when I calculate that, what I end up getting is 1.7 times 10 to the 33rd. Okay. Now I'm going to sum these reactions together to make sure that I don't actually need to do anything else to my equilibrium constants. My nitrogen monoxides cancel out because they're on opposite sides. My nitrogen dioxides cancel out, and what I'm left with is simply oxygen reacting with O2 to make O3. So that's the reaction that I was interested in. Now, instead of just adding these 2 like I did in Hess's law, I added the heats of reaction. Now here, I actually need to multiply my KEQs, my equilibrium constants. So I'm going to take 1.7 times 10 to the 33rd, and I'm going to multiply that by 1.5 times 10 to the 48th, and what I end up getting for my KEQ for this equation, for this reaction, is 2.6 times 10 to the 81st. So in the examples that I just talked about, we looked at 3 different ways of manipulating your equilibrium constant. The first one that we looked at was when a reaction is reversed. So if you reverse a reaction, your equilibrium constant is going to just be the inverse of the equilibrium constant of the original reaction, just 1 over that original value. If your reaction is multiplied by a coefficient, then the equilibrium constant is just going to be raised to a power equal to that number. So in the example, I multiplied my reaction by 2, therefore I needed to raise my equilibrium constant by 2. Finally, if I have a multi-step reaction, the equilibrium constant for the net reaction made of 2 or more steps is simply going to be the product of the equilibrium constants for those individual steps. So in the example, I flipped both of the reactions, so I found the inverse of the equilibrium constant, and then to find the equilibrium constant of the reaction I was concerned with, I simply multiplied those new equilibrium constants together. So those are the ways that you can actually manipulate your reactions and subsequently calculate your equilibrium constant after you have completed those manipulations.